this is a brief review of what we have discussed so far, what we discussed yesterday on decision tree. Okay, so we said that decision tree is a very powerful machine learning tool because we can use this for prediction, okay, for predicting variables of interest, and this is oftentimes used for categorical variables. Okay, but it can also be used for quantitative variables. Now, the problem that we started analyzing last time, we use the cardio data. Okay, there are so many variables here. There are 15 variables, 16 all in all actually, 16. Okay, and the NSP is actually the this is N for normal, S for suspect, and P is for pathologic. This is something to do with the heart of the if I'm not mistaken, the baby inside the mother's womb. Okay, so N, if it's 1, it's the heart is normal. Number 2 is suspect, which means there might be something wrong with it. And number 3 is pathologic, then there's something wrong with the heart of the baby inside the mother's womb. Okay, and we would like to predict this NSP given some qualities of the mother. Okay, so given this, okay, and then I think I gave you the parameters, what this mean, but we will not go again into that. Okay, suffice it to say that these are measurements as regards the mother. Okay, so last time what we did was to, okay, very quickly guys, because we have done this already, just to look at the structure, just to look at the structure of the of our variables. Okay, and we notice here that NSP is integer, and we don't want that. We want NSP not to be treated as a number, but rather to be treated as a factor. Okay, as a classifier. N for normal, S for suspect, and P for pathologic. So we can easily convert that. What we did last time was to create another variable in the cardio object, the cardio file, $NSPF. That means that we're creating another variable NSPF, and it's actually converting the NSP variable into a factor. Okay, so let's do this. Okay, so when we run this again, the structure of cardio, we will now see that there are now 17 variables. Let me click cardio here. Okay, now there are, okay, so now there are, I'm sorry, 1 to 16 of, my apologies guys. It's not 16 variables, okay? It's the first 16 rows that's being shown here. So we now have this variable NSPF. It's exactly the same as NSP. However, NSPF is already a factor. So we can use now NSPF as a factor. And what we wanted to do was to, okay, in machine learning, it's always good to split your data. Okay, when we split our data, we use a portion of the data to model for our model, and then the remaining part, the remaining data, we also test it and see if the model that we had for the other part of the data is still okay. Okay, so that's the purpose of splitting our data, partitioning. We call it partitioning the data. So usually we split it into 2, or of course you can split it into 3. Okay, so you know guys, the function set.seed, it is to make sure that we have the same values as far as randomizing our data is concerned. Okay, so what we did last time was to create an object called partition data, and then we're splitting it. The sample function splits your data depending on how many you want. Here it's 2. Okay, so how many rows do we have? We use the function nrow for the cardio. cardio data. So our cardio data has, let's see, 2126 rows of observations with 23 variables. Okay, you can see it here in our environment window. Cardio, 2126 rows of data with 23 variables. And then replace is equal to true. Now, what does that mean? So it's like getting a, let's say a marble from a container. Okay, when you get one marble, okay, when you say replace is equal to true, you have to put it back. Okay, which means that when you get another sample, that marble which you took can also become a sample again. Okay, so that's what we mean by replace is equal to true. So what we're doing is we are splitting the data into two. One is 80% of the total, and another is 20%. So here we created an object called train. Okay, and where is that train? It's from the cardio object. However, it only includes those of the partition data which are equal to 1. So in PD, in this PD object, R will split your cardio data into two. One having a number of 1, the other having a number of 2. So let's run this, guys. Let me run first the set.seed and then the PD. Okay, so if we take a look at PD, okay, where's our PD there? So let's click PD. Okay, let me view PD. View PD. Okay. Now this is still 2126 entries. Now all the ones here will belong to the first sample. All the 2s here will belong to the next sample. So observation number 5, observation number 14, number 16 will all belong to the second sample, while the rest will belong to sample number 1. So let's call those that have number 1 as train, and those that have number 2 as validate. Others would call this test or testing, training. You can call it any name you want. But let's just stick to the usual train. And instead of using test data, we call it validate data. So let's run this. Okay. So we now have in our environment, we now have our train data, okay, and our validate data. Our train data has 1718 observations, while our validate data has 408 observations. Okay, if you add these two, you have 2126. Okay, 2126. So that split our data into two. Okay, so what we're going to do now is we're going to do decision tree. Okay, because we want to predict the NSPF variable given, for example, a new data, for example, a mother, and we know the variables, the value of the LB, AC, etc. Then we can forecast or we can predict if the fetus inside the mother's womb, if the baby there if the heart is normal, if it's suspect or pathologic. Okay, so this one, this model can actually be used in the medical field. So this is a very useful. This is a practical exercise, because although it might not be it might not concern finance, but I use this as an example because it's a good way to learn machine learning. Okay, so we're going to make use of the party package. We already installed that. Okay, I hope you have installed the party package. And if you want to learn more about the party package, I said last time that you can go to Google and then just type party package, and then it can bring you the documentation. Okay, so if you want to learn deeper, okay, usually the documentation will have examples. Okay, so here, guys, I use the party here. Of course, you can dispense with that. It's okay not to use that. But I just use this party and then double colon to show that this this classification tree, okay, came from this package. So you have to install party package first, okay, and require it before we can have this, we can run this code. Otherwise, if you haven't installed party and you haven't required it or run it, then this code will not work. So very quickly, guys, very quick review. What we did was to regress, okay? We're trying to model NSPF, and we just use the first three variables. Okay, actually, in the next lesson, in the random forest, we're still going to use this data, and then we're going to regress everything. Okay, random forest is a really more powerful tool than a decision tree. Decision tree has its weaknesses, but the next model that we're going to use, random forest, is by far a very, very powerful tool compared to the decision tree. But I want you to first have a taste of what decision tree does. Okay, so last time we did this, guys. So let's generate this object 3.1, and it's a classification tree of the data trained. Okay, remember that we have split our data into trained data and to validate data. Okay, so we're now trying to predict NSPF. We cannot choose NSP because NSP is integer. Okay, it's quantitative. So we just want the factor NSPF regress on the first three variables, LB, AC, and FM. So if I run this, okay, so it's now there. It's a list, large binary tree. It has several elements in it. Okay, so we will not anymore. Anyway, I'll just show what print tree did. Okay, so we studied this before, but let's just go to the plot. Okay. Okay, so this is now the decision tree. Okay, I won't anymore discuss this. Okay, I think we discussed this in greater detail last time. So suffice it to say, guys, that it predicts. Okay, it predicts the NSPF, whether it's 1 or 2 or 3. Here we can see the prediction. The one that has the higher probability, okay, as shown in this histogram, in the bar plots, guys. Okay, that's the prediction, and we followed the tree last time. Okay, any questions about this, guys? Any questions and any clarifications? Okay, if none, guys, I'll proceed. Okay, so no questions. Okay, so please don't hang. Okay, we can do also the simple type, guys. Okay. Okay, let me see my chat dito. Okay, thank you, Rob. All right, so let me continue, guys. Now we can change, we can improve the model, or say we can okay, control for the number of nodes in the model. What are the nodes? Okay, so this is the simple. It took some time to plot. Okay, so this one includes the probabilities. The other one included just the bar chart. The problem with this is that we can't see the others. Okay, but I think this is 0. Okay, so that's okay. So here in this path, the outcome is 0.771. That's 71%. That the fetus, the baby, will be normal. Okay, here it will be pathologic, etc. So the probabilities tell us the predictions. Okay. Okay, please don't. I'm almost afraid this will again, my computer is quite slow. Okay, so as I said a while ago, we can improve the data. We can improve the model. Well, not improve, but we can limit it. We can minimize the model by doing a mean split. Okay, here where minimum split is that 50 here. Mean split means that for the tree to split, there should be at least 50 members of that particular tree. Okay, so we created this 3.1. So let me just run this very quickly. 3.1, and then let's did it run already? 3.1a, okay. And then let's just plot this, okay. So now this one is a reduced form 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Only 12 nodes here, okay. Only 12 we have only 12 decisions here, okay, while the other one had, I think, 17. Okay, so we were able to minimize. Okay, all right. So quickly again, because as I said, this is just a review. Okay, so if you want it more compact, okay, we can make the minimum split to be higher. Okay, the minimum criterion also to be this means is that we want to be this the confidence interval to be practically 0.0001. Okay, so increasing the minimum criterion means that we are increasing the confidence interval. Okay, and that means that you'll have a wider scope, which means that you'll have fewer nodes at the bottom. Okay, so let's create this. Let's call it 3.1b. Okay, so this is a more compact model. And again, let's go to the plot. So you see here, there are only 4. Okay, only 4 nodes. Okay, and then what we did last time was to compare between 3.1 and 3.1a and 3.1b. Okay, so let's do that first here. Okay, so where did I stop? Okay, so first let's test 3.1b with the model trained data. Okay, so take note that the 3.1b is the one with only 4, right? I think only 4 nodes. Diba? Right? 1, 2, 3, 4. So just a simple model. Okay. And what we're going to do now is we're going to, using that model, using that 3.1b, we're going to predict the values of our NSPF. Okay, we created the model, and then we ask what will be the predictions of our model of our 3.1b as far as the NSPF is concerned. Okay, so we run this last time. Okay, and then run both head. Okay, here you can see this is the prediction. Okay, 21133, the first seven elements there. Okay, so we use the trained data. Okay, so the first predictions are 2111133. Okay, and if we compare that with the actual data, so this is our cardio. 21133, right? So okay, we will have to test first. Sorry, we have to use the trained data. So let me, where's our trained data? So this is our trained data. Okay, remember we're predicting the train data 211133. Okay, so the first 7 elements are okay. They're correct. They were correctly predicted. How do I know here? 211133. Okay, so that just gives us the first 6 elements. Okay, here it's 7. The first 7 elements. Okay. All right, then very quickly now. Then of course after we have the we have the model, then we predict, and then we see how is the model. Is the model okay? Is the model not okay? Okay. So what did we do last time? Okay. Now what we did here was to use 3.1a. And we would like to compare 3.1a and 3.1b. Because 3.1a, if you recall, guys, what is 3.1a? It has 12 nodes, right? But 3.1b has only 4. So let's see which is better, 3.1a or 3.1b. In fact, we can also compare this with 3.1. Because 3.1, this is the first. This is our first model, and there were 19 nodes. So let's do that maybe in addition. Okay, so here we're creating a table. Okay, we use the table function. We create a table, tab.1, and what's inside this one? Okay, so for the y-axis, we ask R to predict 3.1a, because we haven't actually predicted 1a, right? We predicted 3.1b a while ago, and call it predicted. And then for the x-axis, we have actual, and then we compare it with the actual value from the train data and SPF. Okay, so if we run this, we have it printed. Okay, in fact, we can run everything at the same time. Let's run everything at the same time. So this was our confusion matrix, and we learned how to interpret this. All the diagonals are okay, which means the model predicted that it will be normal, and then it was actually normal. But there were 131 instances when it was predicted to be normal, but it turned out to be suspect. The actual was suspect, and it was predicted as normal. 109 cases, actually they were pathologic, but they were predicted as normal. So the off-diagonal terms are all errors in the prediction. Okay, so the correct predictions are only the diagonals. So we can compute for that by using this formula. The sum of the diagonals of our table is tab.1a, divided by the sum of the total. So 82% of the predictions were correct, 17% were wrong. Then we tried doing it also with the .1b. .1b, guys, is the one where there are only 4 nodes. Okay, so let's run this. Okay, so we see that .1a was better. Okay, .1a had 82% correct predictions. Okay, .1b only had 80 correct predictions. Now let's see, guys. Let's see. I didn't put here the 3. Okay, so let's copy this.
Excuse me, sir.
Yes, sister. Yes.
And in my error,
Yeah, it's okay. It's okay.
the result is error in table predicted.
In what table?
1e or
1b?
2
Table?
of them is also error.
Maybe it's best for you to. Okay, let me make you all co-host. Okay, so sister also make co-host. Okay, so that you can easily share your screen. Okay, who else? I'll make you all co-host. Okay, sister, kindly share your screen, please. I'll stop sharing first.
Yes, bro.
Okay.
This one. This one for predict.
Okay. That one
Given
A.
that if B, this is attempt to use zero line variable.
Okay, let's see. May I see again that one A? Sister, that one A first. Tap that one A. Could you kindly go up? Tap
Yes.
that one A. Go up again, please. Okay, so predict. Okay, so we were able to predict, right? Go down again, please. Let's see the predict function there. The predicted is equal to predict. Okay. Go up, please, sister. I want to see the predict function.
Predict function, this one.
No, the one up above, please. No, below. After the diagram. Okay, so for that one B, we were able to predict that one B, right?
This one.
Yeah, you were able to predict that, right?
Yes.
Okay, now tab that one A table predicted. It does not run. Okay. All right. Let me see. Sister, could I share my screen again?
Okay.
Okay. Okay. Because sometimes R is very, especially with the. Okay. Let's do this. Let's first separate our predicted value for 1.a. Okay, so let's insert Control Alt I. Okay, so let's copy this. Oops, sorry. Where is that? Oops, where am I? Okay, here. Should be here. Let me insert here for train data.
No screen share.
Sorry. Okay, so let's try first Control Shift I. Okay, Control Alt I. Okay, it's not Control Alt I. Okay, then let me let's create an object p1 dot okay, predicted 1a. Okay, let's create that, and then Alt minus for the classifier, and then let's copy this. Control C, Control V. Okay, so we're creating an object called predict 1a. Okay, and then let me see, type is equal to, okay, should be class. Okay, let me see, class. Let's insert this. Okay, or maybe we could have just inserted it here. Okay, can you try this, sister? P1A. Let's see.
Yes.
Let's see.
Right.
Oops. Okay, we have a problem with the type. Okay, type. If we type probability, then we will have Okay, we don't need the probability. We need the what's the other one? Class or is it factor? Okay, no, not factor. Wait. Because if we just run this, oh wait, why is it try to train that one? Where am I? So sorry, we're using 1.a. Okay, my mistake. So let's use that 1a. And then P1a. Okay. So here we predicted using 3.1.1a, okay, the model with 12 nodes for the train data. Okay, so let's use that here. If I use that here, hopefully this addresses the problem. Let's replace this by predicted is equal to P1a. Okay. So I'm now using this one. Okay. And then let's run this. Okay, I think the tab 1a now. Sorry, tab that 1a. Okay. Okay, sister, this is what we do. Okay, you can do this. So we create an object called P1a. This is predicted 1a. And then we use the predict function, okay, using the first model, the 3.1a. Remember, this is a model where you have 12 nodes, okay? And the data is the train data. Okay, so when we run this, if we run this, okay, you have this. Okay, so these are now the predictions. 1, 1, 1, 2, 2, these are the predictions. So this is now a vector of, let's see the length of, what's the length of P1a? Okay, the length of P1a is 1718. It means that it has 1,718 rows. Okay, and that's the same as your train data. What's our train data? Our train data is there, 1,718 rows. Okay, so we can now compare. We can now compare P1a with our train data. Okay, sister, did you get this?
Yes, po, on the P1A, I get it.
You got this.
Yes.
Okay, and then do this, and then insert this.
Yes, po.
You just copy it from this one.
Just copy.
Yeah, copy.
Still error.
But when you copy, don't use predict 3.1. Use P1a.
Yes, po.
Okay. You use P1a because that's the object that we created here.
Yes.
How did it go? Did it run?
Yes.
Okay, sister.
Okay. Okay.
You should be getting.
Yeah.
Yeah, you should get this.
Yes.
This one. Okay, good, good. So let's just quickly review this. Okay.
But different result is okay po.
Sorry, did you get 82% and 17% the result? 82 and
No.
what result did you get?
Only predicted actual 1, 2, 3, but
Did
the
you run this, sister? This one?
I will try to. Yes po.
Okay, so did you get this result?
Yeah. Only in the above, only three rows.
Only 3 rows, 1, 3, 0, 4.
Yeah, 1, 2, 3. But
Yeah.
the
This one,
zero-
you have to run this one also.
Oh,
This
okay
one.
lang. Because
Okay.
the sum. Okay.
Yeah, that's the percentage.
Different number is okay.
What did you get?
On the row and the column, first is 1298.
1298.
Yes po.
Okay. Did
On
you
the,
129? Did you, sister? Did you run set.seed a while ago? This one?
yes, that's it. I have.
Did you? Wait. 1222. No, this is 1.1b. Okay, wait. 1298, sister.
Yes, 1298, and the column two is 130.
130. Okay, so there's a
Only
discrepancy.
the column 3 is in the same data.
Okay, what's your percentage? What's your percentage correct prediction?
Not yet. I not yet correct the sum.
Yeah,
the
could you
sum.
kindly
Okay.
run this,
Yes,
the sum and the 1 minus sum?
yes. I will copy it. There's some different.
What's the percentage?
The present and the first is 0.817.
817. So there's a discrepancy. There's a little difference. Most probably, sister, most probably the set.seed there did not run. Okay, but it's okay. It doesn't matter. What's important is that you were able to generate.
Oh, yes.
What happened there was that your training data set is different from mine. Because remember, our trained data set was selected at random. Okay, so most probably you have a different set of training data and I have a different set of training data. May I ask, guys, how about the rest? Did you get the same answer? This one, 82% and 17.9%. Hello?
Sir, different po sa akin din.
Different? What's your answer, Robbie?
81%.
Same as sister, no?
However, yung ano lang po, yung decimal is hindi po.
Okay. Pero what was your actual, what was your predictions number 1? Predicted 1 and actual
1262 po. 1262.
Okay, 1262. Okay, so most probably, guys, we'll have different answers because most probably the set.seed did not, maybe it did not run. Okay, so that could be the only reason why we're having different answers, because had we run this properly, okay, I don't know, maybe I made a mistake or I don't know what happened, but so don't worry, guys. It's okay, because what happened now is that we now have a different training and different testing data, but that's okay. All right. So again, going back here, what we did here was to compute for the error, for how much, what was the proportion that was correctly predicted by our model tab.1a. Take note, tab.1a, by our model 3.1a. Okay, this is our model. 3.1a is the model where, recall that, guys. 3.1a is the model, let me plot that. Plot 3.1a is the model where you have 12, okay, 12 nodes, okay, 12 terminal nodes. Okay, these are 12 all in all, 12 terminal nodes. While on the other hand, 3.1b has only 4 terminal nodes. Okay, so we'd like to compare which is the better model. 3.1a, where you have more nodes, okay, more terminal nodes, or 3.1b. So how do we do that? We do that by predicting the values, okay? Predicting the values. Let me put here or. Okay, but let me first see, okay? Maybe I have to put train here. Okay, so let me see if this will. Okay, sister, could you kindly put here predict .1a and then comma train? Okay, maybe that's why your code was not running a while ago, just like this. Sorry.
I will check po.
Sorry, sister, I didn't hear.
I will check it.
Okay, sige. And then try to check it, and then please tell me, once you check it, tell me if it was okay. All right, so now for this one, okay, let's now compare that with the 3.1b. So I think, sister, maybe you put here also train, okay? So predict 3.1b using the train data, okay? And then let's run it again, all right? So 80.2 and 19.7. Did it run, sister, for your 3.1b?
Yes po.
It ran already when you inserted the train
Yes, the train.
Okay. Yeah, good. Okay, I think that was the reason why it was not running a while ago. Okay, so okay, where are we now? Okay, now so we noticed that the one with the more terminal nodes was more accurate compared to the one with just 4 terminal nodes. This is just 80%. The other one had, okay, this one, for me, it had 82% vis-a-vis 18%. Now I'd like to run, okay, let's run, guys, so let's copy this. Let's copy this. Control C, and then let's put it here below. Oops, it didn't copy. I'm copying the 3.1a, guys. Everything here, Control C, and then I'm going to copy it below. Control V. Okay, and then let's call this tab.1. Okay, and then let's use the 3.1. Okay, if you recall, guys, the 3.1 is our first model. Okay, so replace all the 1.1a. Okay, 3.1 is our first model, and it's the model that has 19 19 terminal nodes. Okay, so 3.1. Okay, just to show you guys, just to make sure that that you recall, our 3.1 is our first model. Here, this one. If I run this, the plot. Okay, it's the one that has 17, I mean, not 19, 17. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, sorry. Why 9? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 nodes. Is this correct? This is the 3.1. Yeah, it's a 3.1. And then the 3.1a. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, sorry. Okay, the 3.1a, guys, has more terminal nodes than 3.1. But anyway, let's just see. Let's just see if 3.1 is better than 3.1a as far as predicting. Okay, here I'll just put here predicting train data set using 3.1 model. I just want to compare, guys, because I didn't run this. Okay, so 80.8%. This is quite similar to tab 3.1b. So 3.1a is still the best among the three. Okay, among the three models. Okay, let me pause for a while. Are there any questions, guys? I might be going too fast. Are we so far clear? Kindly reply if it's clear. Thank you, Rob. Sister, questions? Thank you, love. Sorry, sister.
Yes, sir, clear.
Clear, thank you. How about Ron? Clear?
Yes, clear.
Thank you guys. Thank you. All right, so let's move on. Now remember, guys, that we use the train data set, the 80% of the whole data, in order to check, in order to come up with a model, a decision tree model to predict NSP, our normal, suspect, and then pathologic variable. Now we'd like to see if this model will work with a data set that has not yet been seen by the model. When I say that has not yet been seen, it means it's the validate data, because we did not use the validate data in coming up with a model. Okay, so let's see. So here, right here, predict the validate data set using the model 3.1a. Okay, so we're using 3.1a, the model with the 12 terminal nodes, because it's the best of the three. It's the best of the three models that we came up with, the 3.1 and the 3.1b. Okay, so here we're creating an object called P1, okay, P1, and then V stands for validate. I just placed it there so that I know that this is the validate data set. And then we use the predict function, again, 3.1a. We're using the model 3.1a, and then we predict the validate data set. Okay, so let's run this. Validate. Okay, so now these are the predictions using 3.1. if we check the length of P1V, okay. If we check the length of P1V, how many predictions are there? Okay, it's 408. It's correct. 408, guys. Why 408? Remember our validate data. Okay, so our validate data, where's our validate data here? Okay, so let's open this validate data. Okay, our validate data has 408 entries, and then we use the 3.1a model in order to predict, okay, the validate data. So if you can see here, these are the predictions. Okay, so that's 1, 1, 1, 1, 2, 3, 4, 5, 5 ones, and then 3. Let's just check if the first 6 values are the same. 1, 1, 1. Oops, this is wrong. Okay, because the prediction is 1, 1, 1, 1, 1. 5 ones and then 3. So 1, 1, 1, 1, 1. So the first, there are mistakes in the prediction. Okay, the third, the fourth, and the fifth are wrongly predicted. Okay, so let's now see, guys. Let's see the total of the correct and the wrong predictions. Okay, so here we're creating an object called table.1av for validate, and then table. Then it's predicted is equal to, we link it to P1V there. Actual is, so we're comparing it with the validate object, okay? If we use train object here, guys, then it will generate an error term because the comparison, the table should have the same number of rows. That's why I was checking what was the length of P1V. Okay, so let's print everything here. It's just the same as the one above. Print, I mean, run the code. Okay, here we go, guys. Okay, so we used the model 3.1a for to predict the validate data set. And it turns out that the model predicted the normal one. There were 296 correct predictions. It predicted it as 1, and the actual was 1. Okay, there were 2 suspects that were correctly predicted. Okay, these are the correct predictions, as I mentioned a while ago, and the off diagonals are the wrong predictions. So all in all, it was around 80%. Okay, 80%, 79.9, and 20%. Okay, the 3.1a model had 82 and around 18. So it fared well, guys. Even if we used another set of data, the validate data, the prediction, the correct prediction was not quite far off from the model. The model gave us an 82% prediction and 18% wrong prediction. While using the validate data set, which has not been seen yet, so this is the first time our model is seeing this validate data set, we got a almost the same. Of course, there's a difference, but 80% correct prediction and 20% wrong prediction. That's good because that's very close to the model correct predictions. Okay, any questions, guys? Any questions about what we did here? We use the validate data set and check if our model 3.1a, okay, check if our model 3.1a would also be a good model to use for our validate data set. Okay, any questions?
None, sir.
Okay, and just for curiosity, guys.
So sorry, sir. Error again.
Error again, sister?
Yes.
Okay, did you, well, let's see. Where did you encounter your error? Here?
P1P
Then predict?
and predict all of them. So error in regret where new data. I can
Okay.
share.
Yeah, sige. Okay, okay. Sige. Please share. I'll stop share.
Oh my. Where are you? And this one, sir.
Okay. P1V. P1V. Your code is correct. Could you please run first? Just that one. Yeah, just line 103. Just line 103, sister.
Yes.
No, don't run them together.
Okay. This one.
Yeah, just that one. Where object validate not found. Okay, but you have validate there, right?
I have, yeah.
Yeah, you have validate. Yeah, you have validate. Okay, can you use, let's see. I wonder why. Okay, can you use, instead of validate, can you use new data is equal to validate? Let's see. Yeah, in 103, because it tells us that new data is equal to new data. Kindly write new data is equal to validate.
Because I have this one already, yeah.
No, sister, go back to our code.
Okay.
Okay. All right. In row 103, okay, so you have there predict 3.1a, right? Comma.
Yes.
And then write new data is equal to.
New data.
Yes, new data is equal to. Space, okay.
Space.
Okay, equal to.
Equal.
Yeah, equal to. Yeah. Okay, can you run that, please? Okay, still error. Validate not found. Okay, but we have validate. We have the validate data there.
Yes, I don't know.
Yeah, you have validate data. Okay, it's present. Can you just type data is equal to? Do not use new data.
Yes.
Remove new there. Just write data is equal to. Data is equal to validate. No, right there, data is equal to validate.
New data.
Data is equal to validate. No, not new data, but data there.
Data.
Is equal to validate.
Like that, space.
There. Yes. It's okay even without the space. And could you run that? Okay.
Yes, like that.
Now, I don't know. Maybe it has something to do with the version of R. But did you guys encounter that? I don't know if some of your classmates encountered that problem. Because in my case, I don't. Sometimes I put data is equal to, or sometimes I don't put that. But it doesn't matter. It runs. I don't know why it does not run there. Okay, so that's okay, sister.
Yes.
Then let's go to the next. Oh, sorry. How about you run, sister, the percentage, the confusion matrix? Kindly see if it will run.
Yes. Wait a moment. This one?
Yes, not the next one. Below, go down. Go down. Okay, go up. Where is that?
Still error.
Oh, not that one. We run that already. Put also data there. Data is equal to validate.
Like that?
There. Okay, that will run now. Okay. Now it does not give us the class, but rather the probabilities. Okay. So next, 106. You can close that, sister.
Yes.
You can close the output.
Yes.
Click the X there. Okay, and then where is our? Okay. Where is your predicted? P1B.
Not the predicted of
Okay, the predicted for the validate. Go down, sister, please. Go down.
this one.
There. Okay. So validate. Okay. Kindly run that chunk.
Error.
Tab 1AB. Could you kindly go up to what you ran a while ago? Yeah, we used P1B, right? We used P1B, right? So go down again.
The one B.
So tab.1AB is table, predicted is P1B, actual is, okay. Tab 1, so sister, it's tab 1AB. What's wrong with that? Could you run, please? Could you run again? Okay, could you run again row 120?
Yes, sir.
120, row 120, could you run it?
120.
Yes.
Error.
Object, again, date. Error in table predicted. Why does it not see? Okay, can you just replace actual with
Data.
data? Yeah. I don't know why.
Like
Okay,
that.
but this will
Just
did you run it?
still error.
Yeah. Okay, remove data is equal to, remove that. Don't put actual. Don't put actual, sister.
Yes, po.
Don't put actual. Just write just the validate. Row 120. Row 120.
120.
Yes. Remove actual.
Remove actual.
Yeah. Let's just see validate. Okay. So could you run that, please? Okay. Could you kindly go up, sister? Go up to the test and validate. Up where we started. Go to where we created our. Go up, please. Up. Where we partitioned our data. Okay, go down. Where did you partition our data? Go down, please. Go down. Go down. Okay. No. Sorry. Go up. What row did we partition our data? Go up, please. There. Validate. If we run that, then okay, could you kindly run that whole chunk, please?
This one.
No, not that one. Wait, sister, wait. Go up again, please. There. In row 39, can you see the arrow? Row 39, go to the right side of row 39. You can see the arrow, the chunk. There, please. No. The inside our script window, you see the green arrow there. Green.
This one.
Go to row 39. Go to row 39. Okay.
29.
39. 39.
39.
39. And go to the right. Move to the right. Go there, that one, the code chunk.
Yes.
Yeah, could you run that, please? Okay, so you have here your validate now, okay? Okay, I think, sister, I think when you open this, did you run again the validate?
This one.
Did you run again the validate data?
Validate data. This
Uh,
one.
A while ago, when you opened this, did you run again the codes? Did you run this again?
Yes.
A while ago, did you run this again?
This one.
Yeah, that one. Did you run that a while ago? No. Before, when we started, did you run that?
So sorry, this is the trend in my and so
Yeah.
the
Sister,
sound.
my question is, when you opened the file a while ago,
Yes.
okay, did you run that code? Did you run again set that C, the PD, the that row
Yes.
39, 40, 41? Did you run all?
Yes, for this one I
Mhm.
have the data.
Oh, kasi now your validate now has 408 observations. A while ago, I saw that it was not 408. So I think that when you opened your data, your file now,
Mhm.
when we started, maybe you did not run this set.seed. Okay, so let's go now. Let's go down now. Go down. Okay, go now to our
This one.
okay, there. Okay, so run that now, please.
This one.
Yes. Validate still not found. Okay. Why does your validate have only 22 variables, sister? Could you open validate again, please, sister? Could you
Validate
open?
this one.
Yeah,
This
could
one.
you open that? And then go, yeah, please scroll to the right. Scroll to the right, please. Okay, now I see your problem. Sister, you didn't include NSPF.
Oh,
You didn't run NSPF at the start. Go up, please.
I have already yesterday.
Why doesn't it appear
This
there?
one.
When was that? When did you run that?
This one I have the NSPF
Yeah,
already.
when did you run that, sister?
Last week.
Oh yeah,
Last.
but you should have closed that and because that's not no longer in the memory of R.
Okay.
Okay, so that's why I said I think you did not run the codes. That's why your validate does not have NSPF. That's why you're having an error there. Okay, run please, run 34.
Okay.
Okay, run 34. Okay, and then run again the run that again. That set that seed.
I'll run.
Set that seed, the line 39, please. No, go up. What we did a while ago. Yeah, there. Run the right side, the code chunk there. Okay, run that again. Okay, then kindly open validate. Kindly open validate. Okay, go to the right and see if there's the NSPF there. Okay, there. Now there's the NSPF. Okay, so you rerun that, sister, later. Okay, you have to rerun that, and that's why you were having an error. You were having error terms because remember that we used NSPF as our dependent variable, and we regressed it against LB, AC, and the other one. Okay, so did it run?
This one?
Yes. Okay, it will not run yet because you have not run the tree model. You have to run, sister, the tree model.
Remodel all of them.
Yes, yes, the 3.1a.
Yes.
So you run that, sister, okay,
Yes po.
and that will run already.
No.
Okay, no, it will not run yet because you have to go up and rerun your model. You have to go up, sister, go up, and then do everything from the validate data set.
Okay.
Okay, go down, go down, please. Okay. Okay, you run again that 3.1. You run that, please.
This one? What?
3.1a first. No, go up 3.1a. Okay,
This
go
one?
down, no, you have run that already, right?
Yes.
And then go to, you have finished partition data, so you go down. Okay, go down, please. Okay, there, that 3 that ups, there. Please run 51, row 51. Just 51, there. Okay, and then run 53. Okay, so you now have your 3.1, and then go down. Run 3.1a. 61, line 61.
This one?
Yes, just that one. Okay, and then run 64.
63?
64.
Yes.
Okay. All right. So that's our 3.1a, right? Okay. So don't run any more 3.1b. Okay. Okay. You can run 3.1b, please. Run 3.1b. Okay. Just that. And let's not plot. Don't plot it anymore. It's okay.
Okay.
Then you go now to there. You go to P1T. That's row 79. You go there.
Yes.
Have you run that? Okay, so let's go down. We're just running the go down. Okay. And then okay, kindly run that code chunk, row 93 to 96. Kindly run that. Code chunk 93 to 96. Yeah, run that. Okay, so it's now 80.84. Okay, go down. Go down and then run. Okay, no, up, please, up. Okay, now run 10. Okay, there 103 and just 103.
Together?
Just okay. No, don't include 104.
Okay.
Okay, anyway, it's okay. It's okay. Okay. And then just close that window, the output. Okay, so you now have okay, what? And then so we now have 1B. So go down, sister. Okay, row 120. Row 120, please run row 120.
This one?
Row 120, 120, just 120.
120, only in this
120
one.
first, okay? Validate still not found, okay? So,
No.
validate. But you have already validate, right?
Yes. Po.
Okay, sister, let's do this, no? Because could you later on after class, could you please
Yes.
send me your file?
Yes. Po.
Okay, send me that RMD file, so that I can check where the mistake was.
Yes.
Okay, because it will be difficult to to decipher or to see where the mistake was. Okay, is that
Yes.
okay, sister?
Thank you. Yes, sir. No
Okay,
problem.
so sorry about that. We were not able to see why, but guys, so that's one important lesson for us. Okay, so suppose we finished, we ended our session, and then you saved your file. Next session, when you open it, you have to load again the data because it does not automatically load. Okay, so even if you see the output, for example, you did not close the output, and it's there when you open again your R file, it doesn't mean that it's still there. Okay, you will have to there's a way to do it in such a way that you don't have to run the data again. It's using the R notebook, but we haven't discussed that. We're using the R markdown. So the R notebook is a it's a much better way to use R, but we'll discuss that later on. Okay, so sister, kindly send me your file, please. I'd like to check that. Okay. All right, so let's where was I? Okay, so we saw, guys, that when we used 3.1a versus 3.1b, 3.1b only had four terminal nodes. Okay, there were only four classifications, but 3.1a had 12. So you would expect that this would be more accurate compared to 3.1a. Okay, later on, guys, next meeting when we go to random forest, you'll see that random forest is a much improved decision tree, because in random forest what happens is that R will make several decision trees and come up with the best, quote unquote, best decision tree. So we call it random forest, and we were supposed to have an introduction of that today, but something, as I was mentioning a while ago, there was something that that came up with the carrot package. Okay, so just for testing, guys, could you kindly check if your carrot package installs in your R? So just type install .packages. I just want to see if you have problems with this. Okay, carrot. So that's classification and regression training. And could you please tell me if you encountered some problems installing the carrot package? Kindly chat, please, if you had encountered problems. It's taking some time. I downloaded. Good, Robbie. How about the rest? Okay, once you have unpacked it, once you have installed it, could you kindly check if it will load library and then carrot? Okay, kindly check, guys, if it will load. Okay, may I have feedback from you guys, because it does not load in my machine, in my PC. Error. Okay, which is surprising because I was using this last term, the carrot package, and now suddenly it does not load. So I'm having some problems with it. Okay, were you able to load it, guys? Robbie, were you able to load it? Or nag-error ba siya?
Wait lang, sir.
Library ng carrot. How about the rest?
Load, sir.
Nag-load sa'yo? That's good. It's good.
Ay, sorry. Ay, loading po pala. Loading pa lang.
Okay. How about the rest? Sister, love, did you try
Loading po, load.
loading pa rin?
Error on my end, sir.
Error sa'yo, no, love? How about Ronnie?
Yeah, the loading.
Still loading. Okay. How about sister? Nag-load na ba?
Yes, loading. Packet carrot was built under
Yeah. But did you,
person already.
how about library? Library carrot.
Yes, yes. Library carrot
So it,
already.
no error?
No error.
Oh, maybe you have a super machine, sister.
Oh no, just Windows 10. This is library carrot. The packet carrot was built under R version 4.1.2.
Okay, but no error message there.
No
Because
error.
Carrot was built under R version 4.05, but there's an error in my case. Okay, so anyway, because we can't load Carrot, that's why I said that we can't discuss random forest now. Because you know, guys, random forest, by the way, we're going to discuss that next meeting. So your assignment will be to read something about random forest. Okay, what does it do as a machine learning tool? What does a random forest do? It's a lot more powerful than a decision tree. Think about decision trees, thousands of decision trees. Okay, so you have data. Think about thousands of decision trees, and then you come up with a model from these thousands of decision trees. That's what random forest does. Okay, that's how powerful random forest is. Okay, and then when we progress, we go also to XGBoost, which is a lot more powerful also. Okay, in fact, XGBoost as a machine learning tool is one of the popular ones now because it's even more powerful than random forest. But we'll get there in the next few weeks. Okay, now to close our session today, not yet. It's only so we'll have another example of using another data of decision trees so that you'll be really more comfortable with decision trees. And then after that, we have a brief discussion of logistic regression, which hopefully you met in your regression, because we're going to need it for our random forest next week. We're going to compare. So which is the better model if we just use a logistic regression or a random forest? Okay, we'd like to see and find out. Okay, so this one is using the RPART package. Okay, so make sure that you install this first. Okay, so install the packages. I don't know if I have told you to install this RPART, and also please install the rpart.plot. Oops. Okay, if you haven't installed it, guys, kindly install these two packages. And then if you have installed it, please require them. And kindly please inform me if you're done. rpart.plot is for plotting. When you're done, guys, kindly say you're okay. Are you done? Okay, thank you, Rob. Sister, Love, and Ronnie, have you accessed RPART and RPART plot? Are you ready, guys?
Yes, po.
Okay. Sila,
And then library.
sorry?
And then library.
Yes, yes. Okay, access the RPART and the rpart.plot. So this package is also used for partitioning data. It's also used for decision tree. So we'll use this one and try to compare it with the party package that we used a while ago. Okay, we're going to use the same data. Okay, so that we have a comparison. Okay, are you ready, guys? Feedback, please, if you're done.
The library only warning is okay po.
Yeah, it's okay. If it's warning, it's okay.
Okay.
Done, guys? Is it taking long to install and okay? Thank you, sister. How about Love and Ronnie? Are you okay?
Sir, can I share my screen?
Yeah,
Not
sure,
sure
sure.
if it's loading on my end.
Okay, sige.
This one, sir.
I think it run. Could you kindly run that code chunk, Love? I think it run. Could you run just row 199, 129, the RPART?
This one, sir.
Yeah, just that one. Let's see if it will run. Okay. strange. It doesn't give any message, but it's okay. I think, okay. Could you try running 136, row 1, just row 136. Is there a 3 dot? Yeah, there. Okay, it's running. You
Okay.
see there at 3.2.
Yes,
Okay.
sir.
All right. Thank you.
Thank you, sir.
Okay. So let me share my screen again. Okay. Now I did some changes here because I checked our code last week and I had some errors there. So I revised the last part, which I'm going to share with you now through chat. Okay, so here we're using RPART. This is also a powerful package as far as decision trees is concerned. So let's run first this, okay, this 3.2. So take note that I'm now creating another object called 3.2, whereas in the first part, we use the party package. I used 3.1, right? 3.1A, 3.1B. So just to distinguish, I'm creating an object called 3.2, and it's RPART function, okay? A while ago, we used the C3, that's from the party package. And then we're regressing NSPF on LB, AC, and FM. We're using the train data, okay? And then we ask R to print this object, okay? So let's run this. Okay, so it's quite the same as the C3 function a while ago, okay? So it's just a 3. Okay, if you recall, guys, we have something like this, right? And then the asterisks there are the terminal nodes, okay? So let's, instead of analyzing that, let's analyze this. RPART.plot, and then we plot 3.2. Okay, so it will now show the probabilities for normal, for suspect, and pathologic. Okay, there. Okay, so you find here that our part has a better presentation as compared to the party package. Okay, so here you have for this model. Okay, it's the same, guys, as the but it's the model is different. 1, 2, 3, 4, 5, 6, 7. Only 7 terminal nodes. So if you follow this, same thing. If AC is greater than or equal to this number, it's 0.008 something. Okay. If it's yes, then immediately go down here. Okay. If no, then you have to look at LB. Okay. If it's LB is less than 137, if it's yes, you go here to the left. If it's yes, you go to the left. And if it's no, you go to the right. That's the rule here. Okay, but you notice that the presentation, the plot of coming from the RPART is a lot better than the one we had a while ago, the party package. Okay, and then there are several extras that you can put here. Now, if you want to learn more about this, you can Google, guys. You can, let's put here RPART.plot. RPART.plot. Okay. So here you have some, okay, for the type, guys, actually there are, this is limited. You go to the, let me see. You go here, did I highlight it a while ago? Okay, this one. Maybe I'll just share also this one here. Okay, so this is the documentation for our part.plot. Let me just share with you you can, of course, in the chat box, guys, let me share this with you. So if you want to copy this and get this, okay, there, I shared it in the chat box. Now let's just take a look at some portions here. Okay, r.plot here, the extra. Okay, so for the extra, if 0, no extra information. And then for 1, display the number of observations that fall in the node per class. Okay, so it will put there the number of observations in that particular node. And then here, plus 100, okay, so we have 1 plus 100, so that's 101. Okay, it will also display the percentage. So that's where the extra 101 comes from here. Okay, here guys, so extra is equal to 1, 3, etc., etc. Okay, so I'll leave you guys to try to run this. Okay, you'll have different plots. Okay, I think this is the one. Okay, this is the one that okay, so notice guys that this one is quite different already. Okay, let me share this with you. I changed this because I tried to recheck, retest our model, and I had some problems with it. So I revised it. Okay, wait, can you understand this? Okay, so I think you understand this, guys. So kindly copy this and replace the others here. Okay, after this, guys, after the extra is equal to 1, replace it with this one. Okay, and then the codes, guys, put it in a code chunk like this. So here I'm creating an object called P2. Okay, P2, and we're predicting what's 3.2? 3.2, guys, is our model. It's our classification model, a decision tree model, where we use the trained data, right? So that's our 3.2. So we're going to predict that here. Predict. So let's run this. And then here it will be, so this is observation number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then these are now your predictions. 1, 1, 1, 1, 2, etc. If we check the length, how long is P1, P2? How many observations? Okay, 1718. That's good because this is the prediction for trained data. Remember, trained data has 1718 observations. So the predictions should be equal to, in length, in number of rows to the data, okay, which is the trained data in this case. Okay, and then let's compute for the confusion matrix. Okay, so we're creating again another object, tab2, table2, table function. Predicted is equal to P2. Okay, remember P2 is here. P2 is our predicted value. Actual is the train $NSPF, and then we print it there. All right, so this is now the predictions for our 3.2 model. Okay, so there are correct predictions also, and there are wrong predictions here. Okay, correct predictions, the diagonals. And then let's see, guys, how many percent is correct if we run this. Okay, there. 83% and 17%. So it turns out here that the 3.2 model is better than the 3.1A and 3.1B. You have 83% correct predictions versus around 17 wrong predictions. Okay, and then, sorry, this is wrong. This is not predicting train. This should be predicting validate. No?
This is the new one, sir?
Yes, this is the new one. This is the one that I shared with you. Yes. Okay, so please copy that. Please copy that, guys. Copy that. And then, okay, and that's the one that you use. Okay, because the previous one, I checked it and there were some errors. So I modified the code a bit. Okay, so just like the one that we did a while ago using the party package, we will also predict the validate data. Remember that we split our data. In machine learning, you always do that. You don't use everything, all your data, to model it. Otherwise, that would be overfitting. Okay, we call it overfitting when we use all your available data to model it. So usually we split our data. So let's check now our validate data set using our 3.2 model. So we're creating this object prediction to validate. Again, the code is predict 3.2 new data is equal to validate type is equal to class. Okay, so this one, guys, I got it from that's from this data. That's from this reference. Okay, this one. This is a reference as an example to predict your data set in our RPART package. All right, so you see the syntax is quite different. Okay, so new data is equal to validate, type is equal to class, and then let's run this. Okay, so these are our predictions. Okay, and then let's compute now for the confusion matrix and the percentage correct predictions. Okay. Okay, so for our predicted value, okay, for our validate data, it's around 81% and 19%. So it's still better than the Party 3.1A model that we did, okay, a while ago, because in the 3.1A model, I think the validate data set had 79% correct answers and 21% wrong predictions. Okay, did you get this, guys? Any questions? Okay, good. How about the others? Were you able to get it? I'll give you a few minutes, guys, to try. Sister, you have...
Still copy it, not then copy it.
Okay. Sister, it's here. Okay, I place it here in the chat box. Okay, thank you, love. Okay, so take your time. Okay, so it's 7:58. I'm sorry we didn't have a break. Would you want a 5-minute? Is it okay just to have a 5-minute break, guys? Not 15 minutes. Or would you want a 10-minute break, guys? Okay, I'm sure there's so much information overload already. Is that okay, guys?
Yes, sir.
5 to 10-minute water break.
Yes, sir.
Okay, all right. It's 7:58 by my watch. Then we resume at 10-minute break. So we resume at 10:08. Okay, and kindly download already. Let me just show that. Okay, kindly download already the this one, the iris. We're also going to use. This is another example of decision tree, but this will be very quick. And then I don't know if we still have time to do the first part of logistic regression, because we're going to need this in order to compare this with the random forest. Okay, so let's come back after 10 minutes. So we finish our another example of decision tree, and then we go to logistic regression. Okay. So let's pause for a while. Okay, I hope you have opened already the file. Okay, so let's go here. Decision tree, this time we're going to use another data set, but this data set is readily available because it comes with R. Okay, so we have already acquired RPART. So we're going to use RPART again. Okay, and the data that we're going to use is IRIS dataset. I don't know, guys, if you have met this dataset. Has any one of you met this dataset? IRIS. Okay, so this is from the natural sciences. This is a dataset about the leaf, the different leaves. So why don't we access that? Okay, so there are 4 variables here, 5 variables: sepal length, sepal width, petal length, petal width, and then you have the species. Okay, so there are 3 species here: setosa, versicolor, and virginica. Okay, it's not shown here. Okay, so these are the species. Okay, let's try to access it. Let me close this. So here, IRIS, okay. There are 150 observations. This is quite a small data, 150. So you have here the sepal length, sepal width, petal width, and then the species. Okay, this is oftentimes used in logistic regression, where you try to identify which species based on the sepal length, sepal width, petal length, and petal width. So there are 3 types of species. You have setosa, you have virginica, and you have versicolor. Okay, so those are the 3 species. Okay, so our goal here is to be able to predict, okay, predict whether it's setosa or versicolor or virginica. Now, if we're going to use this in regression, then it's called multinomial logistic regression, because you have 3 species. If you have only 2 factors, okay, let's say you have only setosa and virginica, then it's called binary logistic regression. But since you have more than 2, so it's a multinomial logistic regression, and it's more difficult than the binary logistic. Okay, but we're going to use decision tree in trying to predict whether the flower is setosa or versicolor or virginica. Okay, so let's go back to our model, to our code. Okay, once again, guys, let's set the seed. Okay, so this is just any arbitrary number, 9850. I just put there 9850. And just like what we did a while ago, we're going to create 2 samples, okay, where the partition is 70-30. Okay, and then let's view the partitioning of the data. So let's run this. Okay, so this one, guys, okay, it means that observation 1 and 2 belongs to the second data set, and all the ones here belong to the first data set. Okay, so that's very easy to partition our data set. Okay, so let's call the first data set the one whose let's call it training. Okay, the training data set is from the IRIS data set, and we are partitioning. Okay, we are subsetting based on the index. Okay, 1, which means all those that have an index equal to 1 will belong to training, and then it will include comma all the columns, all the variables. Okay. On the other hand, we call the data testing all those that has number 2 for their index. So let's run this. Okay. So we now have 2 data sets here. You have the training data set consisting of 104. Okay, so this is around 70% of the of the iris data set, and the testing consists of 46. Okay, so we have more data for the training. Okay, 70-30. Okay, clear so far, class? Clear so far? Feedback,
sir.
please? Okay, good. All right.
Yeah.
So let's now model. Let's now model this. I'm sure you'll easily understand this now because we have gone through this. Let's create an object called T1. Okay, of course you can use any name. I just use T1, and we're using the RPART function. So this will create a tree, a decision tree, where our dependent variable is species, and then regressed on tilde and then dot. Do you know what this means, guys? Anyone who can explain this? Tilde, because a while ago we used tilde also, right? When we regressed, if you recall, guys. For regression, we use the tilde function when we're creating a model. Okay, where's that? Okay, the tree. For example, here, okay. And SPF tilde. Okay, so this is your dependent variable and these are your independent variables. Okay, for here, guys, tilde and then that. It means include all the variables in this data. Okay, so we're using the training data, guys. So first we're modeling only the training data. And then here, the method is equal to classification. We did not put this a while ago in our model, but it's okay, even if I think that's the default. Okay, so let's run this. Run. Okay, so this is our decision tree. Okay, but we won't go there. Let's take a look at the. Okay, let's take a look at the plot. Okay, so we know this, guys. Our plot. Let's plot this. Okay, so we have here the three factors for the dependent variables: setosa, versicolor, and virginica. Okay, so what does this model tell us? Okay, so we start with the petal length. If the petal length is less than 2.6, we go here, then that should be setosa. Okay, and it comprises 34%. 34% of the data. And then otherwise, if the petal length is not, it means it's greater than 2.6, then no, then we look at the petal width. Okay, we look at the petal width. If it's less than 1.7, then we go here. Otherwise, if it's greater than 1.7, then we go here. Okay, so that's our decision rule. That's our decision tree. Okay, of course, we can improve on that. Remember the extra, which I mentioned a while ago. Okay, so we can run this, Control Enter. Okay, so it not only includes the number. Okay, it not only includes the number, but also the probability. And also this code, the fallen that leaves, is used in order to make sure that the final results are at the bottom. Okay, and there are other functionalities of your rpart.plot which you could explore on your own. Okay, so this is now our model. So very easy, guys, very easy to model using a decision tree, using our iris data set. Okay, and then of course, you know what to do. We have to predict. We have to check if our model is okay. So let's create this object P1 where we are predicting T1. Okay, our data is training. Okay. Now you can see the difference here. Okay. Predict T1. Now take note, T1 is an RPART object, right? T1. Okay, we used RPART object here. So sometimes there's a difference between in the use of predict. Okay, when you're using party or when you're using RPART. So here we're creating our P1. We're using it to predict our T1. What's our T1? That's our model, okay? And using the training data, okay? So if we run this, okay, where's that P1 here, guys? Okay, P1 gives us, okay, it gives us the probabilities, okay? So for observation number 3, Setosa, that's 100%, their prediction. But it's not always 100% there. You can see this, that there are mixed probabilities also. 94% versicolor, only 5% virginica, and 0% Setosa. Okay, so it gives us the values as probabilities. If you want it to be not as probabilities, but as class, okay, you have to include this code type is equal to class. And then once again, if we go to P1, okay, let's print P1. Okay, or we could have just used B1. Okay, so here it gives us the type itself, not the probability. Okay, let me just check our structure. Okay, this is a factor already. Okay, no need to convert this. Species is a factor with 3 levels: Setosa, versicolor, etc. Okay, so let's predict, guys. Let's predict our model. Okay, so this one, we create a table for our predicted for P1 and the actual. Let's run this. Let's run everything here. All right, there. Okay, 35, 36, 31, oh, quite high. Okay, the model was able to predict well. Setosa, versicolor, and virginica, 98% accuracy, and then just around 2% wrong prediction. Okay, so that's a very good model. Okay, and then how about let's predict the testing data? Okay, let's do that for the testing data. So we create another object P2. We're predicting T1, okay, the same model, but we're using the testing data. And then again here, type is equal to class. Okay, let's not view it anymore. Okay, and then let's compute for the confusion matrix. Okay, so let's see there. 91% accuracy and around 9% missed a wrong prediction. So for the training, for the testing data, of the 15 that were Setosas, all were predicted correctly. Okay, of the 14 versicolor, 12 were predicted correctly. 2 was mistakenly predicted as virginica, when in fact it should have been versicolor. For virginica, 15 were predicted correctly. Okay, and then 2 were predicted as versicolor. Okay, versicolor, but in fact it was virginica. So these were the wrong predictions. Okay, so this is quite a in this case for the iris data set, this was a good model. Okay, using the RPART package. Okay, any questions, guys? Any questions? Clear? Is it clear so far?
Yes.
Okay. Now let me pause recording this one. Let me stop recording and then I'll record again because I want to separate the recording for the logistic regression. So before we continue, kindly make sure that you have the logistic regression and the binary data. Okay, so let me stop recording now.